Right, good morning everyone, and welcome back to the second session for the Optimization and Dynamics theme for MSD 780. So just before we get started with the application examples, I'm just going to give you a quick introduction. In the meantime, if you are working on the PCs in this room, you can just download the new DAP BC Dynamic Queue Hybrid Workbench. You'll see it's revision 1 under that DAP BC 2022 folder. So while that is in progress, I'm just going to give a quick recap of what we discussed last week. So we jumped in with an introduction and we gave a bit of a review of the DAP BC workbench. We mentioned that it is a general purpose approach and its versatility made it quite useful for numerical application and also its expandability. So we also have direct access to the function scripts and the numeric procedures, which means that if we want to extend the system capabilities or the DAP BC workbench to include something like optimization, it's easily doable. So we're of course not limited by any user interface. There's always room for expansion with regards to the DAP BC workbench. So speaking of optimization, we then discussed the dynamic queue optimizer that we basically combine with the DAP BC workbench. We mentioned that it's an extension of the alpha-C algorithm, which was initially developed by Professor Jan Snyman back in the early 2000s. So being a gradient-based optimizer, one of the main disadvantages is that it is less feasible for problems where you have noisy data present, and the initial variable has a significant impact on whether the system is going to converge either on a local minima or the global optimum. So it's more inclined to basically converge on a local optimum rather than a global optimum. If you're looking at global optimization, there are toolboxes available in MATLAB for that at the expense of computational costs. So they're usually much more costly than your gradient-based optimizers. These gradient-based optimizers are extremely efficient for complex engineering problems, provided that you have a reasonable assumption with regards to your initial design. So then we also looked at the general definition. So once again, by Snyman and Hay, the dynamic queue optimization can be given as follows. So you have some sort of an objective function that you want to minimize. It's subject to a set of design variables. And it's also subject to a set of inequality constraints and equality constraints. So these constraints are typically complex relations between your design variables, or it uses some sort of a data output to do forward difference methods to obtain the gradient. Whereas with your lower and upper bounds, they are basically your boundary conditions on your design variables. So they are treated differently since they have zero curvature, so they're overall easily computed, as opposed to your more complex inequality and equality constraints. And then lastly, we just mentioned this step limit as well. So we said this is also a value called DML in the dynamic queue optimization that you can change. Typically, it's not very susceptible to values. It's not really very sensitive, rather. So as long as this value is just within the same order of magnitude as your maximum variable range. So we typically leave this at default 1. So then moving on to the optimization examples that we looked at. We did mention a general procedure that was also given as an addendum by Dr. Alex Hay as part of his dynamic queue optimizer workbench in Octave and MATLAB. And we ran through a few basic example problems considering the different or more complex design variables, how the inequality and equality constraints influence the complexity of the computational time and all those kind of things. So today we are going to focus on the optimization and more specifically the extension of DAP BC into this dynamic queue optimizer. So you'll recall from the previous lecture, we looked at examples where we had an analytical formulation available for the objective function. In this case, we're going to use the DAP BC workbench. So if you recall correctly, the DAP BC workbench makes use of a combination of analytical and iterative methods. You'll, for example, see in your dap.m file, it calls the ODE45 integrator when it's doing its numerical integration. So it uses iterative methods, which means we don't have an analytical formulation available for our objective functions. We can't formulate a single line objective function. We instead need to rely on the data outputs from the DAP-BC workbench. So our procedure can be broken up into two subcategories. So this first category is in regards to the DAP-BC workbench, which should first be automated. So you'll notice that when you ran the DAP-BC workbench originally, it asked for quite a lot of inputs. Your folder that contains the models, the initial time, the final time, the reporting time step, all those kind of things. So what we want to do for the dynamic queue optimizer, or to actually perform an optimization, is we first want to automate all of those inputs. And once that is done, then we can start looking at the procedure that applies to the optimization itself. So quickly looking at the DAP-BC workbench, we first start with looking at the dap.m file. Just want to zoom in a bit. Right, so first looking at the dap.m file, we first manually insert the folder name containing the input file so that the system doesn't ask for this each time the optimization runs an iteration. So you'll remember that for the DAP-BC or the dynamic queue optimizer rather, when it does its iterations, it prints out each iteration on the command window. So we basically want to just make sure that we don't have to give it any inputs during this optimization process. So you'll notice in the dap.m file, I commented out this folder equal to input, and I just replace it with folder equal to PR_D. So the pendulum rod model D is the one that we're going to look at today. Of course, if you're looking at one of the other application examples or your own problem, then you'll just replace folder or this PR_D with the folder or the model that you're working with. Then for the second step, we want to comment out the initial condition correction input as well. So you'll notice this is this answer equal to input with regards to whether we want to perform initial condition correction. And I just replace that with answer equal to Y. You can also replace it with N for no, but typically it's good practice to just do an initial condition correction each time the iteration runs. It just makes sure that there aren't any discontinuities in your system before it starts running. So you don't want any problems with regards to your joints not being accurately joined due to machine precision and all those kind of things. So that's just what the IC correct does. So still under the dap.m file, we then also want to manually input our final time. So you'll notice once again I commented out this input line and I just added the t final equal to 3 seconds. So this is once again just a value that I chose based on the application example that we're going to look at now. And then we also want to comment out this reporting time step, and we just want to replace that with our own or a value that will be automated for each iteration. So in this case we chose it as 1 millisecond. Then for the third step, we also comment out the last 2 lines in dap.m, and this just suppresses the display of the number of function evaluations. So once again, you'll recall from the original DAP-BC workbench that if you ran DAP, it basically gave you a bunch of lines that showed the function evaluations over there. So we just want to comment this out so that our output in the command window for the optimization is continuous. And then for the same reason, we just also comment out the corrected initial conditions output. So this is found under the formulation analysis iccorrect.m script. So if I just go to the Octave file, you'll see in the main folder there's formulation, so you can just expand that. Then you can go to analysis and you'll see iccorrect is over here, and those are your last 2 lines. So these last few lines are the ones that you want to comment out from display up to the last display as well. Right, so with that in mind, we've now done all of the automated inputs, and we've basically cleaned up the DAP-BC workbench. So now we can move on to the procedure that we're actually going to use for the iteration or the optimization problems. So typically this first step you'll just apply once, and from there you can then just update your second subcategory each time. So this will differ based on the problem that you're looking at. This one is now your new DAP-BC dynamic queue hybrid workbench. So you don't have to worry about this once you've done it once. Right, so moving on to the second set of procedures. So the first step whenever we do an optimization problem is to identify the parameter that we want to minimize or maximize. And this defines our objective function. So if we look at the DAP-BC problem, we can perhaps minimize actuator forces, maximize accelerations, maximize velocities, those kind of things. So whenever we want to minimize or maximize something, that is a clear indicator that we're working with some sort of an objective function. Then the second step is, of course, to define the parameters that will influence the objective function and the optimization. So these are your design variables. And if I change these values, my objective function is going to update. Then for the third step, in the DAP-BC model files, we also want to assign a variable number to each of the design variables. So considering, for example, if we want to vary the length of the pendulum rod and the mass of the pendulum rod, then we can say that the length is denoted as x1 or xDAP1 in the DAP-BC files, and we can define the mass as xDAP2 or x2. So the reason why we use xDAP over here is just to make a clear distinction between the DAP-BC files and the dynamic queue files. So whenever we're working with the DAP-BC files, we always refer to xDAP, and whenever we work in the dynamic queue files, we always refer to x. So then for step 4, we make sure that the vector xDAP is also defined under the formulation sum files include global.m script. So just quickly going back to Octave, you'll notice, so still under the formulation file, we can head to sum files, and then you'll see over here is include global. So this is typically where you define any variables that that need to be globalized or generalized for all of your input files. So we just define xDAP here at the top, just to make sure that all of the model files can, or the model input files can use this xDAP. So with that done, we then define any constraints, whether it be inequality, equality, or boundary conditions that may be imposed on the data or the variables. So at this stage, it's just going to be a pen and paper exercise. We just want to write down what are the relations between the design variables and the data that we get from DAP-BC. What are those relations that need to be satisfied? Once we've defined that, we can now create a new script and a function which takes in the relevant design variables and outputs the function and constraint values. So this is known as a transition script in the sense that we are now transferring data from the DAP-BC to the dynamic queue workbench, and this is basically the connector between the two. So then under step 7, under the dynamic queue folder, we also want to update fch.m and grad.fch.m based on the data that we require. So you'll recall from the first lecture on optimization, we also said that FCH and grad FCH are your two primary dynamic queue files that you're going to work with. Then for step 9, in the main folder once again, update the optimization.m script to include your starting points, lower and upper boundary conditions, and any other inputs that are not at default. So the difference between the previous lecture, so when we looked at dynamic queue, we had a file over there, optim.m. So we're now not focusing on this optim.m, we're working in the main folder. So we work with this optimization.m file, and this is where we're going to change all of the inputs. So you can ignore that optim.m under the dynamic queue folder. So just moving on then to step 10. Once we've updated all of these things, we've included all of our constraints and objective functions, then we can actually just execute the optimization.m script and we wait for it to run. So typically with the DAP-BC problems, depending on the number of variables and the complexity of the problem that needs to be solved, it can run for quite a while, and it's mainly attributed to the actual outputs that it gets from the DAP-BC rather than the computational effort that the dynamic queue optimizer would require. So it's always just a good idea to take into account how many variables you're working with to sort of get or to sort of gauge how long it will take to solve the problem. Right, so that was just the statement regarding the steps that we're going to follow. So just applying these things then to our example, we can start off by considering the driven pendulum subjected to a constant torque. So as we mentioned before, this is your model PR_D that we're looking at. So from the previous lectures that just focused on the DAP-BC, the DAP-BC outputs and just doing general parameters, not doing any variation of the parameters. This was the general schematic for the pendulum rod that you looked at. So just looking at the forces and the torques and the accelerations as well, this is basically what the free body diagram looked like. So it was a forward dynamics problem in the sense that we proposed a torque and we wanted to measure the acceleration and the velocity and basically all of the kinematic properties. So we're not going to change it from a forward to an inverse dynamic problem. We're going to stick with the same problem. And we're going to ask ourselves questions regarding the design. So what can we vary? What will the effect of the variation be on some of these parameters? So a few design questions that we can ask, for example, is, just zooming in over here. So one of the questions that we can ask is, what is the maximum reasonable acceleration that the pendulum can achieve? And I say over here reasonable acceleration since it has to be constrained or sufficiently constrained to give us a feasible design. Nothing's really going to stop this system if I don't specify parameter constraints to, for example, maximize the length of the rod and make the mass as big as possible and see what the acceleration is at the end. So we always need to ask what the reasonable acceleration or the reasonable objective function is subject to a set of constraints. So then the next question is, how does the initial orientation of the rod influence this value? If I change the starting angle, what will happen? Will I be able to reach a maximized acceleration earlier? What will the effect of that parameter be? What is the influence of the constant torque on the acceleration? So previously we defined that torque as, I believe it was 10 Newton meters. Now we want to ask what is the effect going to be if I change this torque? Also, what would happen if we vary the mass of the system? So that is basically just the mass of the pendulum rod since we're working with a single body mechanism. And then lastly, how does the pendulum length influence the kinematics as well? So what will the effect of this parameter be on, for example, the acceleration or the speed of the system? And one thing that we can do is investigate each of these parameters in isolation or independently. The problem with that is we are not going to get a good representation of what the overall minimum is. So instead we want to ask, can I vary all of these parameters and see what the minimized or the maximized solution is going to be? So these are all design questions which we can then investigate simultaneously using the dynamic queue optimizer. Right, so moving on from that, we can use these questions to formulate an actual design problem. So I've added a few design considerations as well, but in general, what we can define over here for the problem is maximize the acceleration of pendulum body 1, subject to a starting angle, torque, the pendulum rod mass, as well as the length of the rod. So the fact that we say maximize the acceleration already tells us that this is the parameter that, or this is the objective function. This is the value that we either want to maximize or minimize. In this case, it's maximize. Then subject to tells us that the starting angle, the torque, the mass of the rod, and the length of the rod are going to be our design variables that we're going to consider. So just looking at the design considerations, the maximum time that we give this system to reach the maximum acceleration is 3 seconds. We also use a reporting time step of 1 millisecond. So this was already defined, if you remember correctly, in the DAP-BC or the DAP.m file that we looked at. Then we also specify that the starting angle may vary between minus pi and pi. The torque may vary between 3 and 10 Newton meters. The pendulum rod mass should be between 2 and 4 kilograms. And then the moment of inertia of the rod should remain unchanged at 1/12 ml squared, equal to 0.06 kilogram meter squared. And then lastly, the maximum velocity magnitude should also be equal to 20 meters per second. Right, so you'll notice from these that since we know what the design variables are now, we actually have minimum and maximum bounds on some of them. So for the starting angle, it's between minus pi and pi. The torque is between 3 and 10, and the mass is between 2 and 4. And then these last two refer to equality constraints, in the sense that we have some sort of a complex relation between our design variables. So in this case, it's the mass and the length, which must be equal to something. So that tells us that it's an equality constraint. And then the maximum velocity magnitude should be equal to 20 meters per second. So if you remember correctly, this is a forward dynamics problem. So we give it a torque in and we expect to get the kinematics out. So the acceleration, the velocity, the positions, those kind of things. So that means that the system will first have to run the DAP-BC before we get that maximum velocity or that maximum speed out as a, well, basically as an input to the dynamic Q optimizer. Yes. Yes. So basically the values that I gave over here is just values that I define myself. So you can go and look at something like up to or between 0 and 25 Newton meters. You can basically change it to anything you want. This is just the values that I chose, and it's basically just to constrain the system so that it has reasonable bounds with regards to what we're considering. So you might say, in a design problem, you might find that the torque should vary between 3 and 10 Newton meters, subject to some sort of a torque spring or something that you have at the revolute joint. So those will be something that that when you do an actual design, you would refine these values. Yeah. Yes. Yeah. So like I said, I think something like a torque spring or something would change the model characteristics. So you might have a spring that has a certain stiffness, and in order to ensure that the flexibility of the spring is maintained, you have to vary the torque between 3 and 10 Newton meters. If you go higher, then you'll damage the spring. If you go lower, it won't have any impact. So those kind of things will influence the system. Yeah. Right, so with that being said, we can now follow the optimization procedure like we gave under the previous section. So jumping into the first step. Right, so the first step was to define the objective function. And like we said, we want to maximize the acceleration. So the idea is that we obtain the maximum acceleration value from the post-processor or from the DAP-BC workbench itself. So like we said, this is only once post-processing is completed, once the DAP-BC system has completed all of its numerical and iterative methods, that we can get this out. So typically what we want to do is then define a new variable. We just call it max acceleration value. And that is the square root of your acceleration in the x direction plus the acceleration in the y direction squared. So this is just the magnitude of your acceleration. So we define this under post.m since we can immediately get it right after the processing has completed. Then the second step is to define the design variables. So what we said under the example problem is that we have a total of 4 design variables: the starting angle, the torque, the pendulum rod mass, and the length of the pendulum rod as well. And we want to assign a number to each of these variables. So we can say x1 is the starting angle, x2 is the torque, x3 is the mass, and x4 is the length of the pendulum rod. Right, so then we just need to update our DAP-BC input files so that it reflects these new design variables. So remember that we're working in the DAP-BC subfolder, and we're working under the model files. So because we're working with DAP-BC, we don't define x1, x2, but we use xDAP1, xDAP2, and so forth. So you'll notice over here under in bodies, we updated body 1's mass to be xDAP3. Body 1.j is the polar or the mass moment of inertia. So we just updated that according to the equation that we have, which is 1 over 12 ml squared. So this is 1 over 12 xDAP3 times xDAP4 squared. Then our starting angle is the xDAP1 variable that we have over here. And then basically for body 1.r, which is the starting coordinate, we just find that trigonometrically, since we expect that the basically that the orientation and the length is going to influence the position of that center of mass. We just need to account for that under the initial coordinates as well. So this is basically what we did over here. So it's 0.5 times the length times cosine of the starting angle, and that gives us our x coordinate. And over here we have a half times the length times sine of the starting angle, which will give us our y coordinate for the starting configuration. Then under in forces, we also define torque as a design parameter, so we need to update that under the in forces file. So that we basically do here. So we just go to s2.type. We see that's where we define the torque, and we say the torque value should be xDAP2. Right. Yes. So this is PR_D. Yeah. Yes.
So if I understand correctly, so you take the variables from the optimization, and then that, or you define the variables in optimization.
Yes.
Will be used in your normal models for that BC.
Yes, that's correct. So basically, what you do when you define it, so the optimizer is going to use the design variables, but in order for the DAP-BC to change its values, so its accelerations and velocities and stuff, you just need to make sure that the design variables that you define for the optimization are transferred into the DAP-BC. Yeah. Yes, yeah. So there's that's basically the idea behind the transition file as well. Is that you, in order for the optimizer to get input, you need to use the outputs from the DAP-BC. So yeah. Right, so then just looking at endpoints as well. So we just changed points 2 and 3. So these are once again determined based on the length of the pendulum rod. So we just define point 2 as the point at the revolute joint with ground, so where it's going to swing around. And then point 3 is just xDAP4, so just the length divided by 2, and that's on the other end, just for animation purposes. Right, so once we've made all of these updates and we've now defined our properties, or our parameters in terms of the design variable numbers, then we just make sure that xDAP is also defined under the include global.m file. So over here we defined global xDAP. So since that's there, we know that all of the model files will be able to use these generalized xDAP files or xDAP variables. Then the next step is to define the constraint functions that we require to limit. Yes. Yes.
not do that one. Instead of going, like we say, this value and this value must be always less than this value, or it can be like superior to those values because they are like two values.
Yes, yeah.
So how we can define that? How we can make the difference?
So okay, so just to make sure that I understand your question correctly, so you're basically asking your inequality constraint. Do you mean like if it's greater than or equal to something instead of smaller than or equal to? Yeah, so that will just depend on. Yeah, I think I can actually just show you an example. So if you if you have a problem where your inequality is greater than or equal to something, you basically just take your variables to the other side. Like that. So, for example, if we have something that says x1 times x2 times x3 should be greater than or equal to 20. So what you can then do is you just take all of these over to that side, so then it becomes 20 minus x1 times x2 times x3, which should then be smaller than or equal. So it just depends on which side of the equation you write your inequality. So then this will be your inequality constraint, C1 or C2, depending on what we do. Yeah. Right, so then just looking at the constraint functions, so we said we're working with two equality constraints. So H1 we define as V1 max, which is the maximum speed, which must be equal to 20. So we just take the 20 over, so it becomes minus 20, and that should be equal to 0. And then the second equality constraint is the combination or the polar moment of inertia, which is a complex relation between your two design variables. So that is 1 over 12 times the mass, which is x3, times the length squared, which is x4 squared, minus 0.06 kilogram meter squared. And that should be equal to 0. Then we also define our lower and upper bounds based on the design considerations. So our first column contains the design variables that we're referring to. Our second column contains the lower bounds over here. And then same for the upper bounds, in the sense that the first column is the design variable that we're working with, the number assigned to that design variable. And the rightmost column is the upper bounds. Right, so now we've sort of defined this on pen and paper. Now we just need to remember that V1 max is also a value that we get out once the post-processing has completed. So we just want to define the maximum speed under post.m as well. So we just go over here, we say max speed value is equal to the square root of Vx squared plus Vy squared for that body. Right, so now that we've sort of formulated all of our constraints and we've defined the outputs that are of interest, now we can go and create our minimizer inputs.m script. So this one is created in the main folder. So the main folder being, if you just go into Dynamic Q Hybrid Workbench Revision 1, so you don't go into any of the subfolders, and then you'll notice over here minimizer inputs.m. So the basic setup that we have over here is the same as in the mind map. So I'm just going to switch over here. Right, so for the minimizer input, so remember it's a function. So the minimizer input takes some value in. So these are the design variables that we're going to give it in. And it's going to use these design variables to find the objective function value. And over here, we just defined H1. We don't define H2 over here because we can actually directly define H2 under the FCH file. So over here, H1, however, depends on the output of the post processor. So you can go and define it H2 over here as well, but it's also fine to define it under FCH.n. Right, so just looking at the lines over here, so line 3 refers to add path, gen path formulation. So this just ensures that all of the analysis scripts and stuff are integrated for the minimizer folder or the minimizer function as well. Then we use this line include global. So this just makes sure that we define that global or xdap is a global variable. And now we can go and update xdap. So we say xdap is now going to be equal to the design variable that it gets in. So it's xdap equal to value. Then it uses this xdap in dap and post. So each time xdap changes, dap and post or the post processor is going to give you different values. And then the objective function is calculated after the post processing. So you'll notice over here we say objective function is equal to minus the maximum acceleration value. So the minus in front is basically due to the fact that we're working with the maximization problem. If you remember correctly from the previous lecture, we said that if you have a maximization problem, you just times it by -1, so your curve or your function flips over, and then it becomes a minimization problem. Right, so then for H1, that is just equal to the maximum speed minus 20 meters per second over here, which should then be equal to 0 at the end. So these are all the inputs that we are going to give the dynamic queue optimizer. So if we now look at the minimizer function that we want to call under FCH, we basically say f and h1 is equal to minimizer inputs x. So this x value changes based on the optimization and the gradient that it calculates and everything. So this is typically standard that, yeah, so whenever you have a function that it's going to call, it's always going to use x as an input. H1, so h brackets 1, is then just simply equal to h1 that we defined under minimizer inputs, and h2 being a tangible or an analytical relation between the design variables we can define directly over here. So that is just 1/12 times x3 times x4 squared minus 0.06. Remember that we're now working in the dynamic queue folder, or the files and the scripts under the dynamic queue folder. So instead of using xdap, we just use x over here. Right, so then since we don't have any inequality constraints, this line basically tells us if C doesn't exist, just use an empty list for this for the inequality constraints. Right, so now that we've done that, we can, yes. Okay, so let's just go back to the design considerations. So I just want to check over here. So, okay, let me rather just go over here. So basically what we said, and this is from the design considerations, is we have two equality constraints in the case that these things have to be equal to 0. We didn't define anything where it says it should be, there's some complex relation that has to be smaller than or equal to 0. The only thing that we looked at over there was the lower and upper bound on our design variables. So those are treated independently of your inequality constraints. Since they are, it's basically something like x1 should be greater than or equal to minus pi. So we don't have x1 times x2 times x3 must be greater than or equal to minus pi. So these are treated independently. Yes, yeah. So the bounds are treated, the boundary conditions are basically treated separately from inequality constraints. So we don't have any complex relation that says this variable times this variable squared must be smaller than or equal to something. So in that case, we don't have an inequality constraint. We just define these lower and upper bounds in the optimization.m file at the end. Right, so just moving on then to the grad FCH file. So basically what we said in the previous lecture as well is we can choose between analytical and finite difference methods to solve these problems. Now, because DAP-BC uses those iterative techniques, we're not going to be able to get analytical equations for our gradients. You might argue that we're going to get it for H2 because H2 is expressed solely in terms of the design variables. So although this is possible, it would be impractical to calculate this one analytically, but having to calculate the other ones using some finite difference interval, since the finite difference interval already calculates the values for all of the inequality and equality constraints. So we don't want to calculate the same value twice. So instead, whenever we work with DAP-BC, it's usually a good idea to just rely on, so just to rely on the finite difference method. In this case, we stick with the forward difference method. It seems good enough to give us the gradients out. We just need to be mindful of the delta x, which is 1 e to the power of minus 8. So 10 to the power of minus 8 rather. So this value, like we said, it depends on sensitivity analysis and stuff. I did include under the MATLAB file, so under the main folder, you'll see there is a file over here that refers to the sensitivity analysis. So this is just an example. Over here, we just, instead of using minimizer inputs, we used max force funct. So this is just a different function or transition file that we used for this case. But you're more than welcome to play around with this and change the values and everything. So yeah, in general, 10 to the power of minus 7 to 10 to the power of minus 9 is a good idea for the sensitivity or the step size. But you can investigate that, maybe play around with that value, see how that influences your convergence tolerance and number of iterations that you need. Right, so for this case, 10 to the power of minus 8 was sufficient. So then we can just move on to the optimization.m file. So this is, like we said, used to define the boundary conditions, the chosen starting points, and any other default inputs or non-default inputs rather. So something like a different convergence tolerances on our design variable norms or those kind of things. If we want to maybe change the DML, the move limit, we can also investigate that. So just going back over here, so remember optimization is now in the main folder that we're considering. So we did define all of our starting points over here. So this is just a choice made. You can go and play around and see if you change this to pi over 4 and x2 to 9 or something like that, what the effect will be. So will it then converge at the same solution? Will it converge perhaps at a different solution? You can investigate that. So we basically give x0 over here, which is the starting point. We give the lower bounds, like we defined it initially. So we give for x1, the lower bound is minus pi. And then for x2, it's 3. X3, it's 2, those kind of things. And we just do that for the lower and upper bounds. And then for the next line, we just say what is my design variables and what are my design variables and objective functions going to be. If I run denq with my starting points given as x0, my lower bounds LO, my upper bounds up, I use a move limit of 1. And then I specified a slightly relaxed convergence tolerance on my design variable norms, so 10 to the power of minus 3. And then also on my function values, I define this as 10 to the power of minus 8, but it is default 10 to the power of minus 8. So you can actually leave this out and it won't be an issue. So then just another thing that I included, you'll notice under the optimization, over here at line 5, I defined a tick, and then at line 22 I say runtime is equal to TOC, and then that will give you the amount of time that the system ran, or the optimization rather ran, and then you can just divide it by 60 to get the value in minutes, and that gives you a good idea of the computational cost that you're going to need, the time that you need to run the optimization. So since this is a relatively complex problem, it did run for around 23 iterations. Just want to zoom in over here. Right, so it did run for a total of 23 iterations, and we see that since we used the 10 to the power of minus 3 convergence tolerance, it terminated on the step size. And then what's nice about the optimization or the dynamic queue optimizer in the command window, it's also going to give you the equality constraint function values, so the final values of your constraints. So we can see H1, which is 0.012, is quite close to 0. H2 is 10 to the power of minus 6, which is also very close to 0. And then our lower and upper bounds are also given here at the end. So we can see since all of them are negative, except this last one, which is once again basically 0, since all of them reasonably satisfy all of the constraints, we can conclude that the optimization terminated successfully. And then if we just type in X, it will give us our final design variables, and F will also give us our final objective function value. With the difference over here being, since it is a maximization problem, this is now the negative of the actual acceleration. So to get the acceleration for this optimized solution, you're just going to take F and you're going to times it by minus 1, and that gives you your maximum acceleration. Right, so that was mainly the numerical outputs that we get. So if we, so I'm not going to rerun it. It takes around 46 minutes to run this problem. But we do have the graphical results available. So you'll see once it completed its run, it will also print out all of the inequality and constraint outputs that you consider, and then you can just go into the post processor and you can start calculating these speed curves as well, just using the plot in the post processor as well. Just moving down again. Right, so firstly, our optimized parameters we obtain from over here. So phi 1 is this 0.179 over there. So we just times that by 180 over pi, so then we get it in degrees. Our torque at the end is 8.9 Newton meters. Our mass is 4 kilograms, and our pendulum rod length at the end is 0.42 meters. So all of these are within the bounds. So that means it's qualitatively, it once again satisfied all of the conditions that we prescribe. If we now just go to the post processor, we can look at the maximized acceleration curve as well. So this is just the square root of ax squared plus ay squared against time. We can see at the end it is around 1,890 meters per second squared. And then remember, we also specified the speed at, so the maximum speed over 3 seconds should be 20 meters per second. And we can see that at 3 seconds, it reached that 20 meters per second threshold that we have over there. So our initial configuration basically looks something like this. So it starts at a positive angle of 10 point, I think it was 10.3 degrees over there. That will give us our maximized acceleration and optimized velocity magnitude as well. So just something to note is if you do want to plot it, you can basically just go to your command window under the main folder. Yeah, so you'll notice I think it's under dynamic queue out as well. I think it may have changed over here, but the dynamic queue.out file will also give you the values for each iteration. So you can basically just copy and paste it from there. So if I take, I think, the optimized values, so because it's still in its parametric form, we can just type in xgap equal to something like 0.179. And the second one was 8.9378. Then for the mass, we define it as 4. And the last one was the length as 0.4243. So then you can just execute gap and post. So don't worry too much about this global XDAP defined in the current scope. This is usually handled by the optimizer. So this is just typically once you've cleared your variables, it will throw this up. So it's just a good idea each time you run DAP-BC in its parametric form, so where it makes use of XDAP1, XDAP2, just basically clear your variables and stuff before you do another run. Right, so then we can just look at a few examples. So I already coded this in, but this is just to plot the speed of the system. So you'll notice over here, this is basically the speed curve that we got under the mind map. And then we can also look at the second case, which is then it's the acceleration as well. And this acceleration also matches what we expect and what we got initially after the optimization. So just give your design variables as XDAP in. Otherwise, you can just go back and change it in the model files as well. Right, so that basically concludes the example that we did. So yeah, we basically now saw in this lecture how to integrate DAP-BC and dynamic queue. So it's overall, it's basically just making sure that your design variables translate from dynamic queue to DAP-BC and vice versa. And just taking into account that the complexity of the dynamic analysis is going to have a predominant influence on the computational time that your system is going to have to solve. Yes.
Now, I want to know what would happen if, for example, speed one analysis. Let's say, for example, if you have speed, let's say, for example, we go to speed.
Yes.
What will happen?
Yeah. So the analysis. So then you'll, instead of having a 4-dimensional problem, you're just going to have a 3-dimensional problem. So under your inforces.m file, you're just going to change the torque back to, let's say, 10 Newton meters or whatever value you want to use over there. And then you can just, so you just make sure that you then have 3 variables at the end. So you define your 3 variables, and then once you run, most of it will stay the same. So you're just going to rerun the problem then. So it's probably going to run a bit faster then because you have one less variable to worry about. And then it will also most likely give you a different optimized solution since the curvature and the objective function itself, which was dependent on that variable, now changed. So yeah, it's basically just removing that one as a variable, rerunning the optimization. Yes. So if you do a good initial design, or if you choose your initial design in a how can I say, in a savvy manner, then it will converge. It will still converge to some sort of a solution. It might not be the global optimum, but it will most likely converge to a local minimum. Yeah. So yeah, it's basically just changing the dimensionality of your problem. It's not anything major. It's just removing that as a design variable and then rerunning the optimization. Yeah. Right. So so I think that concludes the example that we're going to look at today. So before we end off, I just want to quickly discuss the assignment as well, and perhaps give a few pointers with regards to that as well. So I'm not sure if you guys had a chance to look at the assignment, but yeah, basically here it is. So you once again going to use the DAP-BC dynamic queue algorithm. You're going to use revision 1, so you'll see on the on ClickUp there's a revision 1 workbench over there. So that's the one that we looked at now, that's integrated with DAP-BC. So you need to use that one to optimize one or more features of a planar multibody mechanism of your choice. So the example that we looked at now was a single body mechanism. Typically, we'd like to see multi-body systems. So using more than one body and seeing what the output of the system is going to be, optimize the problem, whether it be an inverse dynamic problem or a forward dynamic problem. So yeah, and then it just refers to you are allowed to modify the MATLAB files as well. You just have to include that as well. So yeah, so then you have to submit a PDF report as well. So typically what we're going to look at for the PDF report is we'd like to see what the initial design outputs look like, and then the optimization process and the outputs, or the optimization results. So you're going to give, let's say you are doing a problem where you vary the length and the stiffness and the mass of a certain body or system. Then you want to include an initial design for your initial design parameters or your initial variable choices. Then also your optimum design. So once your optimization is completed, rerun the dynamic analyzer with those optimum design variables and see what the new graphs and the new results are that you get out. And then it would also be nice to see the optimization histories as well. So like we saw now, where you look at something like the, yes. Oh, okay. Let's see, I think it's, yeah, so this is on ClickUp, and I'm just gonna, right, there we go. So it should be visible now. All right, thanks. Yeah, so you're going to give your initial design results, your optimum design results, and then also your optimization history. So how did the constraint values change? So the inequality, equality constraints, the lower and upper bounds, and your objective function. So but that or dynamic queue is going to give you that as output at the end of your optimization. So if we can sort of get all of those results, I think you'll be sorted. So yeah, and then yeah, so we just also don't want to see an elementary problem. Try to use a multi-body system where you have more than one body. Yeah. So I think that's basically the crux of what we want for the second assignment. Yeah. So any questions? Yes. 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 Yeah. So yeah. So your initial design will be your choice of starting point. So it will show the results and everything. For example, like the torque or the acceleration or something, those kind of plots. And then your optimum design is going to compare it. So what is now the maximum acceleration or the maximum torque and stuff. Yeah. So and then just like a discussion of like the convergence behavior and yeah, I think the plots as well. Did it converge successfully? How did it converge? All those kind of things.
Okay.
Yeah.
Would it be acceptable if we took the first assignment as well and added to that?
Yeah, I think that should be fine. Yes. Yeah. Yeah. So so this is basically just an extension, I think, basically of the first assignment, in the sense that you now just have to do an optimization on the system. Yeah. Cool. Awesome. Any other questions? Yes.
So it's a little bit more, we don't have to necessarily show the change of the input path. It's like we did in the first assignment. It's more just saying this is our initial design, so the outputs, the optimization results, these are, so you compare the results.
Yes. Yeah. So if you used an application, yeah, you can modify the MATLAB files. You just have to include it. But the main purpose of this this assignment is to show that you have variation in your system. You investigated if there is an optimum design to your system. Yeah. Cool. Right. Yes.
Just thinking about my own assignment right now. From assignment 1, I use a bit of a complex suspension system.
Okay.
Is it okay if we use, so I see like all the models I know from that PC example.
Yes.
So for example, with like face and struct suspension, I see that hasn't been changed to make it an optimized formulation.
Yes.
So is it okay if we use a model like that, even though it exists, but then we modify for an optimization?
Yes, if you look over here, it basically says you are allowed to modify any of the MATLAB files, but if you do, you need to submit them as part of your assignment submission. So yeah, I think if you update it and you modify it a bit and you include optimization, then yeah. it should
So
be
then
fine.
it doesn't count as optimization from that line mechanism not being on the example.
Um,
Because the input files kind of exist for the basic room, but
yes.
I just want to find out.
Um,
Yeah, I think um, the one thing that I noted for assignment 1 is many of you only specify, for example, Revolut joints. So it will be nice if you can have a mechanism with more than one type of joint as well. Yeah, but that's more relevant to assignment 1. I think for this assignment 2, seeing that there's not much time, I mean, I think you have until the 13th of November. I think it will be okay if they optimize one of the files for which the input files already exist. I think it will be fine. Right.
Even if it is not that complete.
Well, if you look, if it's, you must, obviously you determine how much you want to put in, and what you put in is what you get out, right? So if it's a very simple example problem for which the input files already exist, and you only do a very simple optimization, you're not going to get great marks, right? So if you use a simple example and this is, yeah, then try and expand on the optimization, you know, do different runs and compare and whatever. Does that make sense? The one thing that I just want to caution you to do is start. This is my strategy for simulation. Start with something simple and then gradually build it up. Start with something simple. Why do you do that? So that start with something where you know what the answer should be. Do the optimization and check that you find that answer. Because then you have confidence in your model. Then you can expand. If you build a very complex simulation with all the bells and whistles and you press the button and it runs and it converges to some answer, you have to trust it in the blind. You might have made a mistake somewhere that you're unaware of. You know what I'm saying? So start with something simple, gradually build it out. In terms of your question, okay, the focus of this part of the module is the optimization. So it can be a simple simulation, but then we want to see that you put in some effort with the optimization. All right, is that fair? You happy with that? All right. Cool.
right. Any last questions? Okay. I think in that case, yeah. So we're done for today. We'll yeah, I'll see you guys in the next lecture. It will also be an in-person lecture, but we'll also do the hybrid approach as we did for this one, where it will be available on Blackboard Collaborate. So yeah, thank you very much.